Welcome to Easy Mathematics and a new video to a small snack. Today we take care of a certain fractional part. You see the expression here, n squared plus n over 10 to the power of the floor of the logarithm n plus 1 to base 10 and the square root out of it. Okay. So the statement is, for every natural n greater 1, there is a natural k greater 0, such that what? Such that the fractional part of our expression is equal to 4.9 times 10 to the negative k. Yeah, so what does this mean? So what we have to do is we want to show that our expression is of the form integer plus 0.00 So we are interested in these 49. And then you see here is n greater 1. So what happens for n equals 1? This is also a question. And yeah, to get a little bit explicit, we take a look at a couple of examples. But before, if you want to try this problem by yourself, here are some hints. So what is the floor of log n plus 1 telling us? And second hint is the Taylor series. And here, the logarithm is to base 10, okay? Yeah, and before we start, I assume that you know about the Taylor series, so I will not talk about that. If you're not familiar with Taylor series, please make sure you see another video and then you can come back. Yeah, and here are a couple of examples. So if we plug in n equals 1, you see here this expression. We have the square root of 11 over 10, and this is and then the square root out of it, and we take care of the fractional part. We get 0.0488 ... And then for n2, 3, 4, we have 0.049, 0.049, and so on. And example n equals 50, we have 2 zeros, and then 49. And for the form 4.9 times 10 to the minus k, we have k equals 2 in the couple of first examples, and then k equals 3. So yeah, you can think about for a formula for k depending on n. Yeah, and now we take a look at the solution. And yeah, the Taylor series, we take care for real x greater 0, and the square root of x, we split x up in the form n squared plus r, where n squared is the highest perfect square such that r is greater 0. And then the Taylor series of square root of n squared plus r is n plus r over 2n minus r squared over 8n cubed plus some higher order terms. We will not take care of them. And so if we plug in our expression into the Taylor series, we get this expression, n plus 1 over 2 times 10 to the power floor minus 1 over 8 times n times 10 to the power 2 times the floor and higher order terms. And yeah, we make a couple of observations. The first one is here this n is the integer part, so our fractional part is determined by the second and the third term and the higher order terms, okay? So it's approximately the second term minus the third term. And there is a second very important observation. The dependency of n in the first term is the digit position, it's not the value, okay? So if you take a closer look at 1 over 2, this is 0.5, and 1 over 10 to the power is 10 times negative to the power. And now we shift the dot, we get 5 times 10 to the negative, the floor of the logarithm of n plus 2, okay? And we see that here the 5 is not depending on n, the dependency is only in the exponent, so this exponent is telling us something about the leading zeros. And the third observation is the second term, this one, is very small in absolute values and it gets subtracted. So 0.0 ... minus very small seems to be 0.0 ... 49. This is our third observation. And the question is it small enough not to affect the 5 in a more critical way? And the answer is yes, it's small enough. And we discussed this right now. So if we take a look again at the fractional part, so first I want to mention the floor of the logarithm of n to base 10 plus 1. We call this s, and this is the number of digits of n in base 10. Okay. So we have approximately the fractional part is 1 over 2 times 10 to the power s minus 1 over 8 times n times 10 to the power 2s, and this is approximately 0.5 times 10 to the power negative s minus 1 times 10 to the power negative 1 times 10 to the power negative of s minus 1 times 10 to the power negative 2 times s. And what happened here? So the 1 over 8 is approximately 1 over 10, so this is the 1 times 10 to the power negative 1, and n has s digits, so it's approximately of the order 10 to the power negative s minus 1. Okay, so please think about that. So we have approximately 5 times 10 to the power negative s plus 1 minus 1 times 10 to the power negative 3s. And now we see when ms gets bigger, we have enough offset of the digits to get the 4.9 pattern. I guess this is easy to see. So we have approximately 4.9 times 10 to the power negative s plus 1, and now we see if we write s plus 1, if we call this k, then we see in our question, so what is our guess for k depending on n, and we see k of n is the number of digits plus 1. And if we take again a look at the examples, they are here, so you can confirm this by yourself, and we see that our our guess was correct, and now we have proven this. Yeah, and that's all for today. Yeah, I hope you enjoyed this video. See you next time. Have fun with it, and bye bye.